Hi everyone, welcome to the Earth Science Regents Review podcast series created by Hommocks Middle School Earth Science Department. Today we're going to focus our attention on ellipses and Kepler's three laws. We ask ourselves the question, what is an ellipse? It's a rounded geometric shape that can vary from a perfect circle all the way through a straight line. Now this is important to Earth science because every object that makes a trip around the Sun, that's part of our solar system, has some sort of an elliptical orbit. It's never going to be a perfect circle. It's going to be somewhat of a flattened oval as it makes its way around the Sun. So how do we measure this? We measure it through a process called eccentricity. That's a measure of how round or how flat an orbit is. And we basically tend to say that objects are either going to be highly elliptical or non-elliptical. Your non-elliptical are going to be round, your highly elliptical are going to be very flattened. So we care about this because this refers to Kepler's first law, which states that all planets move around the Sun, they revolve around the Sun, which is one of the focal points, along an elliptical path called an orbit. And you can see as the Earth is making its way around the Sun, it's not a perfect circle, it's somewhat flattened. So eccentricity, again, is a measure of how round or oval an ellipse is going to be. Now your eccentricity is always going to fall in between 0 and 1. If you get an eccentricity greater than 1, you did something incorrect. And there's no units. Your numerator and denominator, the units cancel out. So a perfect circle is going to have an eccentricity of 0. A completely stretched out orbit, a perfect straight line, has an eccentricity of 1. So that's kind of your benchmark in terms of how to determine the shape of an orbit. So we calculate it by measuring the distance between your focal points divided by the length of your major axis. Now this is a formula you never have to memorize because it's in your reference table. And it's going to be the first formula or first equation that's going to be listed there. So distance between your foci divided by the length of your major axis. So let's get into a quick example here. So you have an orbit, say, of our Earth moving around the Sun. What you're going to do is you're going to make a line, AB, straight through the center of the ellipse, basically through the flattened part of your ellipse. Your focal points are going to be the two dots somewhat in the middle of the ellipse. So those are your foci, and your major axis is going to be line A and B. So that's going to be your major axis in that case. So what you're going to do is you're going to measure the distance between your two focal points. You're going to divide that by the length of your major axis. Just a quick note regarding our Sun is always going to be one of the focal points within an ellipse. You don't have to worry about the second focal point. That's just going to be an arbitrary spot in the orbit. Just always know that the Sun is always one of the focal points within an ellipse. So let's just put some numbers to it. Your XY, your focal distance, is going to be 2 million miles. Your length of your major axis is 10 million miles. You put 2 in the numerator, you put 10 in the denominator, and your eccentricity is going to turn out to be 0.200. You always go to 3 decimal places after the decimal point. Always go to the thousandths place with the eccentricity. So that's a relatively low eccentricity. We would say that's somewhat non-elliptical. It's very circular in nature. So the closer you get to 1, the more elongated your orbit is going to be. Now eccentricity can be found in your solar system data chart, page 15. You'll see all these numbers here. You'll notice that the biggest value given to you there is going to be Mercury. It has the flattest orbit when you compare them to the other planets at 0.206. You take a look at Venus, that's going to be the roundest orbit because it's closest to 0. So it's very important to have an idea in terms of what to interpret with these numbers. The most elliptical orbit you're going to find in the solar system are comets. Comets have the most flattened, the most highly elliptical, the highest eccentricity in terms of any orbit within the solar system. So just have an idea that comets have the most eccentric orbit. Now, according to Kepler's second law now, all planets revolve around the Sun and travel equal area over equal amounts of time. That just basically means that because we have elliptical orbits, you're not going to travel around the Sun at exactly the same speed. So if you look at the left-hand side, you see that shape that's shaded in covers 1 month of time. Well, if we are able to determine the area of that shaded region on the left, it would equal the area of the shaded region on the right here. Even though you'll notice that the 1 month distance is different, because the sun is not the center of every orbit, it's skewed to one side. You tend to travel faster when you're closer to the sun. So when you travel faster, you're going to travel a farther distance. When you're a little bit farther away, you're going to travel a little bit slower speed, and you're going to travel a little bit shorter distance. But if you were able to cover the same amount of area, believe it or not, those two areas that are shaded in are going to have equal areas because it's equal amount of time, 1 month of time. Now, according to Kepler's third law, the closer a planet is to the sun, the faster it moves because the pull of gravity is the strongest. So you'll notice with the position of Earth in this picture, Earth is going to be traveling a little bit slower because it's a little bit farther away. If the Earth was all the way to the right-hand side of this picture, it would actually be traveling a little bit faster because it was a little bit closer. So you have the weakest gravity and the slowest velocity, and you have the strongest gravity with the highest velocity. This also holds true as you travel out through the solar system. Planets that are physically closer have to travel a smaller amount of distance. So Earth, in this case, travels around the sun in a much quicker time than, say, Mars, because Mars is farther away, it's got to travel a farther distance. And you can even compare that with every single planet in the solar system. Okay, you take a look at Mercury, travels around the sun in a much faster amount of time than, say, Neptune, because Neptune's just further away. So that's it for now. Thanks so much for joining me on Ellipses and Kepler's Laws, and we'll talk to you soon.